So good afternoon, everybody. Thanks, Jim, for the kind introduction. I see a lot of familiar faces. Jim today morning said this is like 12th event. So I think at least from our group, we have presented almost around, 10, 11? I might have missed one or two. But we have been a part of this forum and trying to bring all the innovative stuffs, what you can do with the OpenFabrics and RDMA stack. So we have three presentations here. So this presentation today, I'll be sharing with my research scientist, Javi. So we'll focus on the virtualization thing. And then the end of the session, I'll be talking more on the MPI and PGAS. And then after the break, we'll be talking about the big data. So as most of us know, we are in a very exciting phase of the cloud computing. Of course, cloud computing maximizes the effectiveness of the shared resources. But then we need to make sure that the virtualization works properly. That is the key thing. And with respect to the virtualization, now we try to build an HPC with cloud. Now HPC, as you know, stands for high performance computing, and the cloud with virtualization always has some overhead. So the question is how we can bring these two together. That is the big challenge, because if we don't get the performance, then especially the virtualized I/O devices, then it will not be practical. So that is the problem we have been trying to do research on and trying to solve this problem. And then, of course, you can see different kinds of HPC cloud. Let's say we have Amazon EC2, let's say with SR-IOV, single root I/O virtualization, with 10 gig. Different kinds of clouds are also being set up. I don't know whether some of you are aware, this NSF Chameleon cloud. It is actually a project funded from National Science Foundation, and it has been targeted for research on virtualization. Okay, so here there are different partnerships like from University of Chicago, TAC, Northwestern, myself from OSU, University of Texas, San Antonio. So actually there is a test bed deployed here, almost like 650 node with 14,000 cores. And it's a totally reconfigurable environment. So it is primarily, again, targeted for research, not just for computing cycles or number crunching, but to evaluate all different ways you can have virtualization. So if you are a part of any of the US institutions or research labs and all, you should be able to just ask for an account and try to run your experiments there. So please follow this link. So today in the morning, we heard a little bit about the SR-IOV. So this is the technology which is trying to provide the opportunity to do the HPC cloud with very low overhead. So broadly, you can see that we have different kinds of the guest OS. These are the VF drivers. And then going through the hypervisor, we need to map it into the SR-IOV hardware so that each VF can be dedicated to a single VM through the PCI path through. And then this can work with 10 or 40 gig as well as InfiniBand. So the question here is, as we have been seeing, especially through this OpenFabrics, all different kinds of technologies, starting from InfiniBand to 10 to 40 gig, iWarp, RDMA over Converged Enhanced Ethernet, RoCE, they are delivering very good performance in terms of latency, bandwidth, and CPU overhead. And the OpenFabrics software stack is driving all these, designing the system. So the question is how we can leverage that and build the HPC cloud with SR-IOV and InfiniBand while delivering the optimal performance. So that is the problem I'll be trying to focus. So in this context, let me introduce like the AMap project. Some of you might be familiar. We have been working on this project almost from day one of InfiniBand when it was introduced in the year 2000. In the beginning, it was only the MPI-1. All over the years, we have been not only trying to follow the MPI standard, we also have been like expanding into the MPI+PGAS. I'll be talking about that in the next talk. But at the same time, also we have very tight integration with GPUs, mic, and the virtualization. In fact, energy-aware MPIs, all those kind of things are steadily going on. And currently, it's being used by more than 2,500 organizations in 79 countries. And we are steadily, like, just from the OSU site itself, this stack, it has crossed 360,000 downloads. So every week, we get around like 1,000 to 2,000 downloads from all different places all over the world. And at the same time, also, we are empowering a lot of top 500 clusters all over the last 10 to 15 years. Here I give an example, like if some of you remember, like in the 2003, there was a Virginia Tech System X. That was the first InfiniBand system in the top 500. So not only we were a partner with that, and all over the years, we have been working with all different organizations. So the latest one is the TAC, the Stampede system. So this is like it's delivering 5 petaflops. So we have been in the community and trying to push the envelope of the HPC. So this is a very broad overview of the MPI architecture. Not only it has the MPI, it has the PGAS, hybrid MPI+PGAS. Again, I'll be talking this a little bit later in the second talk. But then we have a diverse APIs and mechanisms, support for all different networking technologies, InfiniBand, IOAP, Rocky, OmniPath, as well as for all these accelerators. Now for this talk, we'll be mostly focusing on this component, which is the virtualization, SR-IOV, and some of the basic shared memory mechanisms. So this shows like our MPI project, kind of like the downloads over the years, steadily increasing over the years. And since the field is moving so fast, we have actually different optimized versions of these libraries for different environments. Because all this technology, if you think of InfiniBand, the GPU, mic, everybody is trying to optimize on their own ways. So what we have done is, of course, the basic one is the MPI 2, but there are some optimized versions, like with PGAS and all this, the MPI 2X. With GPU, we have the GPUDirect RDMA. We have also version for mic. Also, this is the energy-aware thing I was talking about earlier. So for today's talk, just now, this talk will focus on this particular version, which is the purely targeted for SR-IOV, OpenStack, the containers, SLURM, those kind of things. I'll be talking here. So broadly, we have 3 designs along this line to exploit the virtualization. So the first one I'll talk about this is with SR-IOV, and then is the IVSMEM, which is a shared memory module, and it can work not only on a standalone mode. We also have an integrated version with OpenStack for easier deployment, and then we are working on these other 2, which is the SLURM and with containers, so they will be released in the near future. So this is the public version which we released several months back. This is to exploit the virtualization. So it has full support for SR-IOV enabled InfiniBand networks. It can do the high performance communication. I'll show some numbers towards the end, and locality aware MPI communication. It can also have some auto detection of IVSMEM device in virtual networks, and with a lot of other features like support for integration with OpenStack. So the broad thing, some new things, of course, any MPI stack can run in a virtualized environment. Okay, because it's a virtualization, you can just put it in the VM, but the question is, are you getting the performance? That is the big question. And the performance also becomes more important. Let's say you are running multiple VMs within the node, because now we have multi-core systems. So most of the time what happens, these VMs, how do they detect that they are running on the same node? Okay. In a typical MPI stack, if some of you are familiar, we have a lot of shared memory designs, optimized shared memory designs, which give very good performance within the node. So in order to achieve that, what we did is here, like we introduced some newer modules, like the IVSMEM, which offers a shared memory-based data access across core resident VMs. And we also introduced new things called locality detector and communication coordinator. For example, let's say, some of you know the virtual machines has migration. So let's say I migrate one VM from one node to the other node. So let's say there was a VM A, and then B and C were here. So now the A has moved to this node. So how does A detect that, oh, I am sitting next to V? Okay? And if it can detect, then it can exploit the shared memory communication to deliver you better performance. Okay? Otherwise, all these VMs think that they are totally independent kind of things, and they cannot exploit better performance. So that is the kind of designs we brought in the first phase. And then what we did is, this is the tight integration with the OpenStack. As most of you know, the OpenStack is gaining a lot of momentum for deployment of the virtualized the stack. So what we did is this, we primarily modified this Nova module in the OpenStack so that people can just very quickly have the deployment with our MPI-2 and OpenStack. So both these are actually deployed already. I mean, in the sense it is a part of the release, so you should be able to just download it and then run it with either on a standalone mode or in the OpenStack mode. So the next two directions which we are working on to have the virtualization in a very tight environment or integration with SLURM, because SLURM is very commonly used in all the HPC systems. And then the new thing which is coming with the Dockers and containers, we also want to deliver similar kind of performance. So with this, here let me hand it out to Jiawei Lu. He's a research scientist in my group, so he will try to cover the remaining parts.
Okay, thank you. So Dr. Panda just mentioned we did this work for standalone MPI-2 and also integrated with OpenStack. But the problem is that in many HPC clusters, OpenStack is not there, right? But the SLURM or other like Tokyo or PGAS kind of HPC scheduler is available. So then we have this motivates to say that whether HPC clouds can be built with MPI-2 word and on top of SLURM or Tokyo, this kind of HPC schedulers. So then the question is how to build a SLURM-based HPC cloud with near-native performance for MPI applications over SR-IOV-enabled InfiniBand, and what kind of requirements for SLURM to support SR-IOV and SLURM provided in HPC clouds, and then how much performance benefit can be achieved for MPI primitive operations as well as applications. So in order to show this, I give a very some typical usage scenarios when you launch VMs in HPC clouds through SLURM. So first is like we call exclusive allocation a sequential job. This is like a traditional way you run MPI jobs. You get the allocation exclusively and then run your MPI jobs there. And the second scenario is that you may get exclusive allocation, but you may run your jobs concurrently, right? And then third scenario is like, because we talk about HPC cloud, right? Resource sharing is a very important issue there. So probably some hosts get shared by the allocations, and then it means that multiple VMs from different users may run on top of the same host, and then the jobs also running concurrently. So in this case, how we can manage the SR-IOV devices and the SHMEM devices, right? And also achieve the isolations. So then we see that there is a requirement to manage and isolating virtualized resources of SR-IOV and SHMEM in the context of SLURM. But this kind of management isolation actually is not easy to be achieved by MPI library alone, because your MPI instance, one MPI instance job actually doesn't have the global picture of how resource gets allocated or scheduled for different users, right? But it may be very easier for SLURM because SLURM has this information, the picture, global picture for the resource being allocated. So then we see that we efficiently run the MPI applications on HPC clouds needs SLURM to support managing SR-IOV and SHMEM resources. So we want to see that can critical HPC resources be efficiently shared among users by extending SLURM, and through this, whether we can provide bare-metal performance for end applications on HPC cloud. Okay, so now I just want to give a quick high-level overview of the workflow of running MPI jobs with MPI-2 word on SLURM. So this is like a SLURM-D and the SLURM control-D architecture. So then typically when we submit a job, we need the SBatch file as well as what kind of VM environment you want. So when you send the request, get the physical resource nodes, and then after this you need to launch the VMs on top of these nodes, so that there's some functionalities we need to provide. For example, we need to select the SR-IOV first function, SHMEM devices, and network setting up, and also we need to get the image from the image pool. For example, here maybe we save image in Lustre or other part of assistance, and then we launch the VMs, check and also mount the global storage extra, this kind of things, and then run your MPI jobs, get the results back. This is just some functions and the workflow we should provide. And then how we design this. So we come up with a design based on SLURM Spunk plugin. Maybe some of you are familiar with this. So here we propose 3 different components inside a SLURM Spunk plugin. The first one is a VM configuration reader. This mainly when the plugin gets loaded, we need to read the VM configuration information and then register these options so that this information are visible to all allocated nodes. And then we during the when we launch the jobs, the VM launcher component get loaded and executed. So in that phase, we'll set up VMs on each allocated nodes, and especially we'll select the free SR-IOV first function exclusively, and also dynamically assign the InfiniBand devices to the VMs. And then when the job's done, we will tear down the resources. We tear down VMs and reclaim the resources. So the benefits of plugin-based design is that it can provide very good coordination. So especially with global information, SNRM plugin can manage SR-IOV and InfiniBand resources easily for concurrent jobs and multiple users. And also it can be very high performance. You can do fast coordination. And maybe we can also do something like SR-IOV and InfiniBand aware resource scheduling inside SNRM, maybe. And then the scalability is also good because we can take advantage of the scalable architecture of SNRM and the fault tolerance, permission things, and the security things we can also get from the SNRM plugin-based design for SNRM architecture. So now let's take a look at some numbers. So we did some performance studies on three test beds. One is our internal small cloud environment we call the NowLab Cloud. Here we have FDR InfiniBand with SR-IOV support. And then we also did some experiments on top of Chameleon Cloud, what Dr. Panda mentioned earlier. And then we do similar studies on Amazon EC2. We just want to see that whether where we stand for the performance. But note that in Amazon EC2, they just provide 10 gig with SR-IOV support there. So we evaluated with point-to-point communications and also some applications. So here, let's take a look at the latency and the bandwidth for internal and inter-VM communication. So as we can see that if we compare it with default SR-IOV scheme, we see that we can achieve up to 84% or 158% benefit for latency and the bandwidth. And then when compared with the native environment, we almost only have like 3 to 7% overhead for latency, or 3 to 87% overhead for bandwidth. And one interesting thing is if we compare it with EC2, like the block line shows, we can like give up to 160 or 28. I mean, this type of performance speed up for latency and the bandwidth. And if we take a look at the internal communication for latency bandwidth, we also see that our compared with native, we're also less than 10% overhead. And it is also much better than EC2 environment as well. For application numbers, similarly, we see like for NAS, like 1 to 9% overhead, and then for Graph 500, like 4 to 9% overhead. And then we did a similar evaluation on top of Chameleon Cloud. So here for Graph 500, like less than 5%, and for Spec less than 10%. So this is something we have done with SNRM. And then because recently, some of you may know that containers, especially for Docker, is becoming very hard, right? So because container-based solutions provide lightweight virtualization technologies, so it becomes very attractive, especially when you want to build high-performance cloud. And then we also want to try whether it's actually you can get good performance, especially for HPC Cloud built with container, built with MPI, built with InfiniBand. So when we run the MPI applications on this environment, we see some bottlenecks. We'll show in the next slides how the performance looks like. And then can we propose some design to overcome this bottleneck? And with our design, whether we are able to deliver near-native performance for different container deployment scenarios. And finally, through these studies, we see that whatever we proposed for VM environment, the locality-level design actually can be very helpful here as well. And we can enable both like a CMA, this like a kernel-based communication mechanism, and also shared memory channels for MPI communications across co-resident containers. So let's take a look at the performance, like I mentioned earlier. So for example, if you run the MPI library, by default running with container like Docker here, you see that the green line shows that the performance actually is not good, especially for internal inter-container communication. And then we did like a locality level designs, and we improved performance. We said, okay, good, we achieved like 81% benefit for or 191% benefit for different case. Okay, and compared with native, with this very minor overhead. And for the collectives, this slide shows the collectives. We show the or reduce and or gather. Similarly, compared with default, we can achieve like a 64 or 86% benefit. And then compared with the native, very minor overhead is there. Typically less than like 8 or 9%. And then here we do some application studies on Chameleon as well. This is like 64 containers according 16 nodes. We see that compared with default container case, is like 11 or 16% difference. And then compared with native, is less than 9% or 4% overhead for LAS or Graph 500 respectively. So it means that the optimized container support is actually a promising way to build HPC Cloud maybe. Okay, so this solution will be available for the upcoming release under AMap H2 Vert package. So I will switch to the Panda for the talk conclusion.
Yeah. So broadly, what we showed in the earlier slides, that the main thing is the performance. So I think let me just again reiterate here, if some of you didn't get it. Like in all these charts, we are trying to show three bars. Okay. So one is basically the default. So that is the default MPI you just download and then run, and then the right one is the actual native, that is without virtualization. So that is the best you can get from the InfiniBand. Okay. So all these three things are running on the same hardware. Okay. And then the middle one is what is the optimized in that container support. So this is exactly what we are trying to show, that from the default you are trying to not only get performance benefit, but it is very close to the native. And that is the kind of the thing, the message we want to give to the community, so that with this new design, we are trying to make the virtualized environment come and running very close to the native performance. So if you are willing to tolerate like only a few percentage, 1%, 3%, 9%. The earlier it used to be very big, like 25%, 30% kind of things few years back. So that's how the HPC and cloud were not coming together. But now with all these new solutions, it is more practical, and that's what we trying to work here. So for the timing, this version, if you are trying to run it with the OpenStack or an integrated standalone manner, you can do it. And then in the near future, we'll be releasing this support with the SLURM and with the container. Okay. So with this, let me stop here. If there are any quick questions, either myself or Joe will be happy to answer.
I have two quick questions.
Sure.
The SLURM solution, did you have to change SLURM at all, or is it just SLURM as it was out of the box?
Yeah, we don't have to. You just have to load the SLURM plugin we provide. Yeah.
And on the, you said that the next release of MPI H2 Vert would have the container support. What's the time frame on that?
Next few weeks. Okay. We have just started testing as of today morning. So if it goes through everything, you will get it very soon. Any other questions?
These are all the intranode or the performance slides are all intranode or also internode?
No. So there are different kinds of numbers. So let me explain to you. So let's say for this one, it is intranode. Okay, intranode intercontainer. But here it is more collective. Like we are trying to run it on 64 containers across 16 nodes. So that has both internode as well as intranode. And then the application, of course, it includes everything together.
Okay, so one additional question: the user space interaction directly with the HCA does or does not go through the supervisor, the hypervisor?
On which one? The SR?
Well, with this scheme, going from a VM to the HCA, go through the hypervisor?
You want to answer that?
Sorry, I didn't quite get the question. Can you repeat?
Like user space directly to HCA.
Okay.
The user library transactions.
So if you go, that path is like a default SRV path. We didn't change anything. Whatever, okay. Because mostly what we did is for the internal inter-VM communication enhancement. And for SRA pass, we do some tuning for that. That's all. Yeah.
Right.
Okay. Any other questions? Yes. Yeah.
Is all this code open source or is it closed source?
At this point, this
Yeah.
particular version is closed. So what is going to happen, that's what I indicated. I mean, things are rapidly changing, so we are just trying to provide the solution. Once these things are stable, then we'll try to consolidate those things. Okay. Yes.
Help us understand the performance numbers. So internode 180 with containers, 181% decrease. Can you go back to that slide? So 191%.
Yeah, so this is the intranode performance, intranode intercontainer, and what we are trying to show the bandwidth between, like, this is the default versions versus this is the optimized version, what we are trying to.
So this is with RDMA, HCA, or?
Yeah, these are all running over the basic native InfiniBand.
Okay.
Yeah, these are all InfiniBand numbers.
Okay, thanks.